Today we will discuss simplest model for determination of electron hole concentration in extrinsic semiconductor. Today, part 1 of this lecture will be discussed. So in simplest model for density of free electron and holes, influence of valence band is neglected. If we calculate density of free electrons, then influence of valence band is neglected at low temperature. So here we have conduction band. This is bottom of the conduction band edge, and then we have donor levels. So this model is applied at low temperatures. So for N-type semiconductor, it consists of a conduction band, and below which there are ND donor levels per centimeter cube of energy EI, and influence of valence band is neglected. So we assume that at T is equal to 0, all donor levels are filled with electrons. At low temperature, only a small fraction of donors are ionized. And it is expected that Fermi energy level lies about halfway between the donor level and bottom of the conduction band. So we assume that EF lies more than few kT below the bottom of conduction band, then density of electrons in conduction band is given by NC, and this must be equal to the density of ionized donors. So density of donor levels are represented by ND. The density of electrons is given by NC is equal to 2 pi me star kT upon h square to the power 3 by 2 e to the power EF minus EC upon kT. This is equation number 19. So this is in continuation with the previous lecture, which we have discussed earlier for improved model for determination of electron hole concentration in intrinsic semiconductors. So from there, this equation number 19 is here. When if T is increased, the impurity atoms gets ionized, so that density of ionized donors is equal to density of electrons in conduction band. Therefore, the density of empty donor level is equal to ND within bracket 1 minus FEI, which is nearly equal to ND e to the power EI minus EF upon KT. This is equation number 20. So if we equate equation number 19 and 20, then we'll be able to get the location of Fermi energy level. So equating equation number 19 and 20, left hand side is equal to right hand side, taking log of this equation, and after simplification, we'll get EF is equal to EC plus EI upon 2 plus KT upon 2 log of ND upon 2 into 2 pi me star KT upon h square to the power 3 by 2. This is equation number 21, where Me star is the effective mass of an electron. So substituting value of EF from this equation number 21 to equation number 19, then it leads to NC is equal to under root 2 ND 2 pi me star KT upon h square to the power 3 by 4 e to the power minus delta E upon 2 KT, and this is equation number 22, where delta E is equal to EC minus EI, that is ionization energy of donors. Similarly, density of holes in valence band can also be determined by neglecting influence of conduction band. So in simplest model, in determining the density of electrons in conduction band, we have neglected the influence of valence band. So in determining the density of holes in valence band, will neglect the influence of conduction band, and similarly NV can be given by equation number 23, which is under root 2 nd 2 pi mh star kt upon h square to the power 3 by 4 e to the power minus delta E upon 2 kt, where delta E is the ionization energy of acceptors. So it may be seen from above equations that NC is directly proportional to under root of ND, and therefore log of NC is directly proportional to 1 upon T, and also NV is directly proportional to NA, and log of NV is directly proportional to 1 upon T. So this graph shows the representation of logarithmic of the density of conduction electrons versus 1 upon T for an impurity semiconductor containing different donor densities ND1, ND2, and ND3. And here ND1 is less than ND2 and is less than ND3. So variation of logarithmic of density of electrons versus 1 upon T can be represented by this equation, and location of Fermi energy level can be given by this equation. So in the next lecture, we'll discuss the location of Fermi energy level in extrinsic semiconductor. That is the part 2 of this lecture, and these are the references.